So good afternoon. We will start with this next topic, Fourier series method using this window. So we were discussing about the FIR filter design, right? So if you look into the differences between the FIR filter designing, what we were discussing yesterday, we discussed about this Fourier series method. So without window and with window, what is the difference? The thing is that you will only find that this step 3 and 4, they are the additional steps. Okay, so first you have to draw the frequency response, we all discussed. Then we have to calculate the HN, okay, of the filter what you want to design. Then we need to calculate the window coefficients, we need to calculate the window coefficients while we want to use this window. Okay, now you have this window coefficients Wn. So there are some specific formulas that are there. You just have to put the values of the small n and the capital N, and you are good to go. So you have to calculate the Wn. Then the next step is to calculate H dash n, which would be your desired frequency response, which would be your desired frequency response. And how will you do it? So you will be doing it by multiplying Hn and Wn. Okay, so yesterday we have calculated a lot of values, say h of 0, h of 1, h of 2, and so on. So when you are trying to multiply it, so it will be with h of 0, you have to multiply w of 0. With h of 1, you have to multiply w of 1. With h of 2, you have to multiply w of 2. Okay, and this should become your new hn. So this should be h of h dash 0, this should be h dash 1, and this should be h dash 2, and so on. Okay, then again, the once you get this desired values, then again you have to find out the z transform of the h dash n, what we discussed yesterday, and lastly we have to realize the filter whatever method you like. Okay, so now the types of windows, there are many types of windows. However, there's 5 types of windows, they are very common. So the first one is the rectangular window, and if you see the rectangular window, it is having Wn equals to 1. Okay, so using the rectangular window or not using the rectangular window, it is basically the same. Okay, there will be no change. Okay, then next is your Bartlett window, which is also regarded as the triangular window. So this is the equation. Over here, capital M is nothing but your capital N, which is basically the order of the filter. Okay, so you have Wn equals to 1 minus 2 of modulus of small n minus m by 2 divided by capital M. Okay, similarly we will be having Hanning filter. Okay, Wn equals to 0.5 minus 0.5 cos of 2 pi n by capital M. Okay, so then we are having Hamming window. So Wn equals to 0.54 minus 0.46 cos of 2 pi n by capital M. Okay, and lastly we are having Blackman window. So where we have Wn equals to 0.42 minus 0.5 cos of 2 pi n divided by capital M plus 0.08 cos of 4 pi n by capital M. Okay, now if you look into the shape of these windows, rectangular windows, see it looks like just like an rectangle. Okay, if you look into the Bartlett or the triangular window, it looks like a triangle. Okay, goes up and then comes down. Then we have Blackman window. If you see, it is having a Gaussian distribution like thing. And then we are having a Hamming window where it is similar to the Gaussian windows. However, in the Blackman, if you see, it starts with 0 and ends with 0. Herein it is not the case. Even this what do you call, this value, it will be having some heights. Okay, the starting and the ending values, they will be having some heights. These coefficients. Okay, why this is so? If you look over here, here the coefficients are same. So this minus this, it comes out to be 0. Okay. However, in this case, it is somewhat different. If you see, 0.04 has been added from here and 0.04 has been subtracted from here. So because of this mismatch in these coefficients, so, or the constants, so we are having the raised value over here. Okay. Yeah. Yeah, and then again Hanning. Sorry, this one was the Blackman window. Sorry, and Hanning is here. So, but the reasoning is same. If you see over here, it starts with 0 and ends at 0. Okay. So the shape of the Hamming window and the Hanning window, they are similar. Whereas in the Blackman window, it you uh, get a Gaussian distribution of the coefficients, window coefficients, right? Now, these are the differences between these different types of the windows. So, if you look into, we are basically more inclined towards the how the main lobe and the side lobe they perform. Okay, main lobe is basically the passband region. So, in the rectangular window, if you see, we are having the narrowest main lobe. Okay, in triangular, this thing we are having wider than rectangular window. Okay, then in Hamming, wider than triangular window. So in Hanning, similar to Hamming but slightly wider. Okay, and lastly Blackman, we are having the widest main lobe. Okay, so rectangular, it will having the narrowest one, triangular slightly higher, Hamming higher than the triangular. That means it is higher than both the rectangular and the triangular. Then uh, Hamming and Hanning, they will be having the same thing, but this Hamming window, it will Hanning window, it will be having slightly wider main lobe as compared to the Hamming one, and lastly the Blackman will be having the highest lobe. Now, coming to the side lobe attenuation, why this is so important? Because higher the values, so if you see, we are having minus of 13 dB, minus of 26 dB, that means there is a separation of the signal component. And in the side lobe, what we are intending to do in the side lobe, basically those are the rejected frequency components. Okay, in the side lobes we intend to reject those frequency component. So higher the values of the side lobe attenuation, the better is the frequency suppression over there. Okay, the better is the frequency suppression over there. So among all of this, if you see, the best side lobe attenuation, it is with the Blackman window, followed by the Hamming window, followed by this Hanning window, then triangular window and rectangular window. For regular practical applications, what happens is that we generally use, in most of the books you will find that for biomedical applications, either Hamming or Hanning windows, they are preferred. Okay. So application, they are for the general purpose. Then in this rectangular window, triangular window, signal processing for smoother transitions. So in Hamming window, so we use it if there is if you want to do the spectral analysis requiring high side lobe attenuation. Okay, so then useful for reducing spectral leakage, Hamming window. And lastly Blackman, it is having high dynamic range applications. Okay, then in advantages, simple and computationally efficient, because as you all know, you are multiplying with a value of 1. Okay. And the next one, in triangular one, reduced side lobe compared to the rectangular one. Then good side lobe suppression, lower side lobe suppressions as compared to the rectangular one, and excellent side lobe suppression by the blackness. So overall you will find, so in comparison to the rectangular one, all the other windows they are giving a good suppression of the rejected frequency components. Okay, and that is also ये legible when you analyze this side lobe attenuation values. Okay, then disadvantages: high side lobe, poor frequency resolution, because the frequency components which are meant to be rejected, some of the frequency component they will be getting into your filtered signal. Okay, moderate side lobe attenuation, wider main lobe than the rectangular and triangular window. So what happens is that when you go towards the cutoff frequency, the ripples at the discontinuity or the cutoff frequency, it is higher if you are having a very wide ये lobe. Okay, so that is one of the major problem. Then next is higher side lobes compared to the Hamming window, then widest lobe and poor frequency resolution over there. Okay, so if you see, in all of the cases there has to be some uh, balance which has to be maintained, and in most of the cases if you see this Hamming and the Hanning window, they are somewhat making some balance. Okay, now over here the next figure, it shows the amplitude response of these windows. Okay, amplitude response of this windows. Now in the previous slide what we discussed about the shape of the windows. Okay, we discussed about the shape of the windows, and here if you see, we are dealing with time domain. Okay, we are dealing with time domain. That means when we discuss about the shape of the windows, these windows are created in the time domain because we want to filter out the signal in the time domain. Okay, on the other hand, when you want to analyze the signal, you basically are interested in the frequency domain. Hence, the analysis of these what you call window functions can be better performed in the frequency domain, and hence this figure, the second figure, if you see, we are having magnitude versus the frequency component. Okay, so you need to keep in mind, and whatever we have discussed, if you analyze this figure, you will find it that it is the same thing. If you look over here, this rectangular window, here the suppression is not minimal. If you are saying it is having a very, if you draw an average line, if you see from here, you are having a higher a very least suppression. Okay, so this is the 0 dB gain, that means the gain is 1. So from here this distance is the lowest. Then we talked about Bartlett. If you see 26 here, so just beneath that we are having the Bartlett. Then we are having this Hanning, Hamming and the Blackman window functions, if you see. And again this lobe, this is the lobe, you can see. So whatever we have discussed, you just match this and you will be able to understand what we have discussed till now. Okay, so this is the main lobe basically. Okay, this is the main lobe, and these lobes, after this roll off, these are the side lobes. Okay, again some of the advantages and the disadvantages of this thing in some depth. Okay, so you can go through this. We have already discussed this. Just for your convenience for writing in exams, I have given this one. So benefits of using windows in FIR filter design. Okay, the first is the reduced spectral leakage. Okay, as I already told, that what happens, the frequency components that are to be rejected are compressed over here. Okay, so the less amount of the rejected frequencies will get into your filtered signal. Okay, then by choosing a specific filter, you will be able to control the side lobes of the output signal. Okay. Then, since you are able to what you call eliminate the unwanted frequency in a better way, so there is an improved frequency resolution. Then there would be smoother transitions in comparison to the normal FIR filter or the filter designed with rectangular filter. Then design flexibility. There are a lot number of window functions that are available, and you can use any of the windows as per your need and requirement. Okay. So less ripple in the passband and the stopband filters that I already discussed. When since there is an smoother transitions, so what is happening? There is an averaging effect onto the signal component, and hence in the what do you call it, in the pass band and the stop band, whatever the ripples are being formed, they are getting smoothened out. Okay. Then these are simplified filter designing as compared to the IR filters, and overall we will be having an enhanced filter performance. Okay. Now let us take an example how to solve the problems. Over here, if you see, design design a LPF using rectangular window by taking 9 samples of WN and a cutoff frequency of 1.2 radian per second. Okay. So you need to understand over here is that when we talk about 9 samples, that means the length is 9. So the capital N, it could be 8. Okay. So this is the first thing. Then your cutoff frequency, it is 1.2 radians per second. Okay. Then considering this, so these are given in the equation, in the question. So next, let us calculate what is our transfer function. HD omega, it is equal to e to the power minus j omega alpha in the cutoff region of this thing, otherwise it is 0. Now in our last class, if you see, we have discussed about what? We have discussed that our amplitude should be 1, but today I have changed it to e to the power minus j omega alpha. So why this is so? This is because you will see at a later stage when we are incorporating this into this integral, so we are getting a function something like this, and finally instead of getting sine of omega c n divided by pi n, we are getting a function sine of omega c n minus alpha divided by pi n minus alpha. Okay. And if you look into the this filter coefficients Hn values, what we have calculated, now we have to apply the L'Hospital's rule at n equals to 4. Okay. So what is happening? In our last class, we have been discussing about the shifting of the n values. First, you calculate the n values, then we have to shift the n values after you have calculated the coefficients. Okay. But by employing such a minor tweak, what we are doing? We are basically eliminating that extra step. Okay. We are basically eliminating that extra step. Now again, if you look into the modulus of this one, what would be the modulus? Again 1. E to the power minus j theta, right? If you find out the modulus, it will be again 1. So we are not deviating with our assumption. Okay. But by introducing this factor, we are able to eliminate an extra step what we have learned in our last class. Okay. So same formula, you start to put in over here minus omega c to omega c. Now instead of hd omega, we get e to the power minus j omega alpha. So e to the power j omega n. So as you put in, we get e to the power j omega n minus alpha. So then you perform the integration, and over here you get the integral solution. Okay. Now what happens? What is alpha? Alpha is nothing but it is equals to n by 2. Alpha is equal to n by 2. Okay, or you can say L minus 1 by 2, whatever you want to say. So we get alpha equals to 4. Okay, now you have all the things, just change the values of n and you get this filter coefficients. In the next level, what you have to do, you have to find out the coefficients of the Wn. So for 9 coefficients, so it will be varying from 0 to 8 and all the values are 1. Then in the next step, HDN would be H dash DN, it would be HDN. So these values multiplied by WN values, what we have calculated over here. And then after you get these values, then you find out the transfer function and the perform the Z transform to get the transfer function. Okay, so this is it for today. So I would first like you to uh, do this numerical on your own and see where you are facing the trouble. And again, yeah, this is the same equation with say band pass filters and Hanning window. Okay, so the process is the same, so I am not going into that. So thereafter, what I would ask is that once you practice this one, then you go to these equations and calculate the coefficients for Hanning and the Hanning window. Okay, so your n would be, again we will take it as 9. Yeah, not 9. Yeah, capital N equal to 8. So length will be 9. Okay. Any questions?